Thanks, Jeff. And I would like to thank, first of all, IPAM and the organizers for the chance to come to this wonderful workshop. So yeah, I will talk about something that is actually quite topical, given that there was already a talk on this yesterday by Tomohiro. And it's based on a paper with Jimmy He from basically last year. And so if anybody wants a take-home message from the talk, it's essentially this equality of pictures here. So this is, in some sense, the reason for the correspondence, at least at the level of vertex models. So yeah, if you want to zone out now and just remember the pictures, then basically you have the take-home message. All right. So I will try to spend most of the talk explaining in more detail what's actually going on here. Okay, so first of all, I'll spend some time just defining the basic notions that are needed to state the correspondence. Probably a lot of this was already stated yesterday in Tomohiro's talk, but nevertheless, I'll just go through things once again. So, of course, Schur measures and the Schur process. This is quite an old topic already, dating back to early 2000s in the work of Okunkov and Reshetykhin. And the basic idea is you have a Cauchy identity for Schur polynomials, which is shown here. And you can use that to assign a probability measure to partitions. So essentially just take a single term in the summation here, product of two Schur functions, and then normalize that thing appropriately by the right-hand side of the Cauchy identity, and that defines for you a probability measure. And it's well known that this particular measure, and when viewed as a stochastic process as well, has a lot of nice properties. Probably the nicest property is that if you take a partition lambda and actually use the well-known bijection to project it to a collection of points on the integer line, this actually ends up defining a determinantal point process on the integer line. So in particular, you can get determinantal formulas for the correlation functions of this process. And that has some fairly immediate generalizations. So probably almost everyone here would know that if you take a Schur function, there is a nice property on it, which is known as the branching rule, that effectively allows you to take your starting alphabet in n variables and to split off the variables one by one, and you get a formula such as this. So here the summation is over a string of n partitions that satisfy the property known as interlacing. And the summand is just a product of skew Schur polynomials in a single variable. This is a very simple quantity. It's just the power of x, basically, when the two skew partitions satisfy interlacing. And if they don't satisfy interlacing, it's equal to 0. And this has actually many other equivalent formulations. It's actually equivalent to writing a Schur polynomial as a sum over semi-standard Young tableau. So using this kind of way of splitting the Schur polynomial up into this product of skew Schur polynomials, there's a very natural way to refine the previous measure, which is shown here at the bottom of the slide. So essentially, instead of having a single random partition, I'm going to have a string of random partitions, as shown here, and they're related to each other up to these interlacing conditions. So what's shown here is normally known as the ascending and then descending Schur process. So essentially, you start off from an empty partition, and then you build up this upwards interlacing sequence, and then at some point, you start going down again. Okay, so this has a nice pictorial representation, which is shown on the next slide. And again, this is also very standard and very well studied. So effectively, you take your string of interlacing partitions, and you view those as being diagonal slices of a three-dimensional object, which is a plane partition. And the correspondence is illustrated on this slide. I think it's fairly evident how it works. So basically this, this particular slice here, this corresponds to the first partition in this string. And then the next one is the partition 3, as shown here, and then so on and so forth. And if you do it in this way, you indeed get a string of partitions that interlace upwards to the central diagonal slice, and then they start to interlace downwards as well. And so because of the previous probability measures that were mentioned, you can then put very nice probability measures on this class of objects and go ahead and study all kinds of properties of these, in particular limit shapes. So this is a very well studied area, and I'm sure that many people in this audience know this much better than I do. All right, so what I'm going to talk about is basically ways that you can q-deform these probability measures. And there are really, I guess, two natural ways, or at least two natural ways of doing this. And the first way dates back to a paper of Alexei from 2006. And that was to define something called the periodic Schur process. And again, the definition of this process stems essentially to an identity of symmetric functions, which is the Cauchy identity that is shown here. So what's happening in this particular formula is you have, instead of a product of two skew Schur functions, instead of a product of two ordinary Schur functions, you have the skew analogues. And again, you have two alphabets x and y. And you take a product of these two things, sum over all partitions lambda and mu. But if you just do this, you find that there is some convergence issue. So just computing that sum, as stated, will not do the job. You have to introduce some factor here, which is some analog of a winding fugacity, or a temperature parameter, if you like, that will actually regulate the sum and allow you to, well, the sum to actually converge to something meaningful.
Michael, why do you put mu and not lambda here in the power?
Well, no reason. I mean, you can put either.
I get different sums, right?
Yeah, so this is entirely equivalent. So yeah. All right. So this identity, this is actually in MacDonald's book. So like a lot of things, there are all kinds of hidden gems in MacDonald's book, and you have to sort of read through the pages very carefully. So I didn't actually know originally this was due to MacDonald, but indeed this is an exercise that he does there. He starts off from the skew Cauchy identity for Schur polynomials and effectively iterates it over and over again. And if you do that, you end up getting this, indeed, this nice factorized product here. Okay, so I'll represent this right-hand side by this notation pi sub q here. But yeah, just try to remember, I guess, what it is. It effectively has this object here, which is a very familiar looking Cauchy kernel for people who know the theory. But there's an extra factor here, which is effectively the Euler generating function for partitions. And this extra factor is actually quite important. So, okay, so using this this formula, you can then go ahead and again attribute some probability measure to partitions, and effectively all you do is you just drop the sum over lambda, and now look at the corresponding object, and again that thing as written here will indeed sum up to 1 when you restore the summation over lambda. Okay, so this is going to be our first probability measure that is sort of a q-deformation of just the regular Schur measure. And then there is a second one, which is also topical for this talk. And this one effectively follows as a special case of a family of measures that dates back to Alexei and Ivan's work on MacDonald processes. So effectively, you take the McDonald processes and specialize one of the variables there, which is this t parameter, equal to 0, and you then get what are called the q-Whittaker measures. So this is slightly different. So no longer do you have Schur polynomials. You have these functions here, which are the q-Whittaker polynomials. I'm not going to write their definition in this talk, but these are some very nice objects. They have many nice combinatorial properties, much like the Schur polynomials. But one thing that's very different about these polynomials is they're not determinantal. So Schur polynomials, you have determinant formulas for basically everything. But these polynomials, absolutely nothing like that. They're much more complicated. Nevertheless, when you go ahead and compute this sum here, you do get nice factorized right-hand side. And I'll denote that one with a capital lambda sub q. All right, and once again, you can go ahead and define probability measures using this Cauchy identity. And this was effectively pursued to great length by Alexei and Ivan in their paper on McDonald processes. And there are many nice stochastic processes that arise as various limits of these. Okay. In particular, q-TASEP and polymers and many others besides. Okay. All right, so I guess you will have all seen this correspondence yesterday in Tomohiro's talk, but let me restate it here. So in what follows, I will let lambda 1 be the largest part of a random partition. I'm not saying yet what distribution I'm drawing the random partition from. That's because there'll be two different distributions. So lambda 1 is the largest part, and there will be an additional random variable here, which is just a q-geometric random variable. So probability of chi being equal to k is given by this simple formula here. And that extra random variable is kind of important because of that. There's this extra Euler type product that I alluded to in the periodic Schur measure, and that's somehow resurfacing in the appearance of this random variable here. So this is kind of a technicality, but you need it. All right, so this is the theorem from the work of Imamura Mucciconi and Tomohiro from 2021, which is essentially this remarkable match between these two objects. So on the left-hand side, I take a random partition that comes from the periodic Schur distribution, and I ask what is the probability that the largest part is bounded by capital M. So capital M is some finite integer. I can choose this to be whatever I want. And on the right-hand side of the correspondence, I look at, again, a random partition taken now from the q-Whittaker measure, and I shift it by this extra independent q-geometric random variable. And I say then, what is the probability that lambda 1 plus chi is less than or equal to m? And it turns out that those two sides are equal for all m. So this particular result has some profound consequences. It means that certain observables that you might like to study on the right-hand side here, for which there is no determinant formula, can actually be expressed in determinantal form by virtue of the determinantal structure of the periodic Schur process. Okay. Are there any questions at this point?
What if you're after other parts of lambdas?
If you're after other parts of lambdas, then there's fairly little that can be said at this stage.
On the left-hand side, everything is determinant.
Sure, yeah. Obviously, yeah, I have thought about this problem and many other people besides, I'm sure. Yeah, I have nothing to say at this stage. Yeah.
But in your language, you said there was more than one such thing. You said some events on the right can be expressed in terms of, but then there's only one. Is that the answer? Or not?
Right, but that's correct. But this is actually this contains a lot of information here. So for example, this will tell you about the distribution of, say, the rightmost particle in the q-TASEP. Okay, so yeah, and then all the sub processes of this, you can obtain similar statements. Yeah. All right. All right. So the previous statement is kind of expressed in probabilistic language. I am not by trade a probabilist. I started my life very squarely in vertex models and integrability, exactly solvable models. So for me, it's always helpful to re-express things purely as statements in symmetric functions. So all I've done here is just re-express previous statement as an identity of symmetric functions. And then I will try to prove this thing directly using the vertex models. Okay. So I really haven't done very much here. Yeah. So on the left-hand side, again, there's going to be some sum over product of two skew Schur polynomials. There'll be two sums here over lambda and mu. And note that this sum here over lambda has the constraint that lambda 1 is less than or equal to m. That's coming from the m that appeared in the previous statement. Okay? So in particular, this is a bounded sum, which is quite foreign normally from when you deal with Cauchy identities. Sort of the whole thing that makes Cauchy identities have nice expressions is their infinite sums. They're sort of some far-reaching generalization of geometric series. So as soon as you truncate things, you have absolutely no right to expect that you'll have nice formulas. Okay, and then on the right-hand side, again, product of these q-Whittaker polynomials, and there's this extra factor here. That's coming from this q-geometric random variable that I mentioned on the last slide. And once again, very important to note, this is a finite sum. Okay. All right, so one thing you can say immediately is look at the case where m goes to infinity. Okay, so you're free to do this. And in that case, you know that the statement kind of has to trivialize because on the previous slide, if you take m to infinity here, this is kind of a void statement, right? So something has to trivialize here, and basically that boils down to the fact that those two Cauchy kernels that I defined previously, they're actually equal to each other up to this additional Euler-type factor. So the m equals infinity version of this correspondence is a triviality. So the whole crux of the matter is, can you prove that it holds for finite m?
Why do you say it's a finite sum? You say nothing about the other sizes of the parts. It's a truncated sum, but it's not finite.
So I should clarify. This side is finite, yeah, but this side is infinite.
In what way is that finite? You look at all partitions where the first part is bounded by m, but it says nothing about the other parts.
Oh, I'm sorry. Yeah. So
The number of variables is finite.
number of variables is, but also there's this property here of this Schur polynomial. If the bottom partition exceeds the top partition, then the thing vanishes.
No, but you have accountably many lambda here, and you can have all kinds of mu which sit inside of it. Let's see why this is a finite sum.
Yeah.
Just restricting the first row doesn't restrict lambda to finite set of partitions.
Right, but lambda 1 is the largest part of the partition, so.
No, the left-hand side is infinite because on the right we have q in the denominator, so maybe that is...
Yeah, exactly. So I'm saying that this side is finite, but this side should be infinite. Yeah. So and precisely what Leo said.
Why is the right-hand side finite?
Because number of variables is finite.
So you still have infinitely many.
No, the number of rows in the
The
partition.
number of variables here is
You're
finite.
restricting the vocabulary. Okay,
Yeah,
so
yeah. But actually, even this is not strictly necessary. So you could.
well, if you had an infinitely many x's and y's, it wouldn't
If you have infinitely many x's and y's, then what you say is correct. Then it's
okay, so that wasn't clear from me from the beginning. You're only dealing with finitely many x's.
Yeah, I'm sorry. Yeah, I should have made it more clear. I mean, previously, maybe at the very start, I'm dealing with finite alphabets. So, yeah. Okay. All right. So hopefully everyone is happy with the statement, more or less. Okay, so now I will try to construct the proof. So the proof, at least, yeah, we actually have two different proofs of this result in the paper. So the second proof actually involves generalizing the correspondence. So I'll talk about that briefly at the end. But the first proof is really using some vertex model terminology, some technology from vertex models. And yeah, so this part I think hopefully is quite pleasing for an audience that likes vertex models. And the correspondence actually makes use of something that a priori looks like it should have absolutely nothing to do with the previous result that I showed. Okay, so effectively, what we're going to talk about now is this multispecies TASEP on a ring. Okay, so this has already been mentioned in at least one talk. Leo's talk, he spoke about this. So what you do is you consider a system of particles. They have different colors, as indicated here, and they're hopping around on this ring according to some rules. So it will be a ring with n sites, and every single site will be occupied by a particle, which can have a color, taking values in the set 1 up to m, or it can be occupied by a hole, which would be equivalent to having a 0. And the exchange rule is something quite simple. So basically, you look at two neighbors in this ring, suppose these two sites here, and you denote this by occupations mu I and mu I plus 1. And they're going to exchange with a rate, which is either equal to 1 or t. So there's some exponential clock here, which is ringing with a certain rate. And that rate will depend on basically the difference between the colors, the two colors of the particles here. So you look at the sign of the difference of those two colors, and that will then tell you whether the rate is 1 or t. So let's suppose the difference is positive, then it's going to be rate 1, and if the difference is negative, then it's going to be rate t. And if the two colors happen to be equal, then the exchange is kind of meaningless anyhow because then nothing happens. Okay. All right, so people have studied this system in many works. So I have definitely not made any attempt to cite all of the works where people have studied this question. But the stationary distribution, an explicit formula was given for this in this paper from 2008. And effectively, the kind of algebraic structure that they use there was something called a matrix product ansatz. So what you do is you take a product of operators. I'm not really saying what these operators are, but there's some family of operators whose indices will correspond with the occupations in your ring. So as I go along this ring here, suppose this is a particle of color 1 that would correspond to the operator a sub 1 in this product here. So I take a product of these operators, and I perform then a trace. So you should think of these as being some matrices. A priori, you don't know whether they're going to be finite dimensional, infinite dimensional. So you're going to take some product of matrices, perform a trace, and you hope that by such a construction, that will actually recover the probability of having this configuration in the stationary state. And they actually did this successfully in this work and gave a very explicit construction of these matrices. Turns out that they're actually infinite dimensional and rather complicated. So I'm not going to state the formula here. So my own entrance into this particular topic came in the work with Luigi Cantini and Jan in 2015. And what we tried to do was take the previous probabilities and generalize them by introducing extra parameters into them. So when you introduce the extra parameters, a priori you may lose contact with probability, but you get closer to some nice algebraic object, which are the non-symmetric McDonald polynomials. So effectively what we did was to define a family of polynomials that satisfy two basic properties. The first one being that if you take this f, which again is indexed by one of these TASEP configurations, and you act on it with a Hecke generator. So the formula for this is given here. This is known as the polynomial representation of the Hecke algebra of type an-1. So I can take this operator and apply it to one of these polynomials. And the rule is that under that action, you should get the same polynomial back, but two of these sides exchange, which you can see already starts to mimic what happens in this process on the ring. So somehow this ti here should be some deformation of the generator of the process. And likewise, there is a further relation. Actually, I don't know why I say likewise. It's quite different. It's very non-trivially different, and that is where you take, the object f here, with the alphabet being in the normal order, and then what you do is you cyclically permute the alphabet and insert a factor of q in the first argument, or I guess what was formerly the last argument. And simultaneously, you cycle the elements of the composition in the other direction. And in the process of doing that, there's a factor of q. So that very mysterious looking operation actually has a root in the theory itself. So this actually comes from looking at the affine Hecke algebra construction, or I guess the double affine Hecke algebra construction of non-symmetric McDonald polynomials. So this kind of action is quite natural in that context. And so actually, even though it's not clear, it turns out that these two properties here uniquely define the family of polynomials. And furthermore, when all of these elements of your particles on the ring, if they satisfy this ordered property here, so namely mu is a partition, one can actually show that f mu is a non-symmetric McDonald polynomial. Okay. Any questions about anything here? Okay.
So again, the mu's are the particle location?
That's correct. Yeah, that's correct. Sorry. Yeah, I heard your question, knew what you were answering, and then answered yes, without actually answering your question.
You remind me what the mu's are.
Yeah, the mu's are the colors. Yes. Yeah. Yeah. It's jet lag. I'm sorry. Yeah. Okay. All right. So what we did in the same work then was then basically to construct explicitly a matrix product formula for these f's. So as I said, these f's, you should think of them as some sort of generalization or deformation of those TASEP probabilities on the ring. Okay, and the deformation is the inclusion of these x parameters that was not in your original process. And also there is this q parameter, which was not in the original process. So by setting q equal to 1 and all of the x's equal to 1, you should actually get back down to the original steady state probabilities. Okay. All right. So we actually gave then an explicit formula for the matrices that sit inside of this product here. So notice that they're deformed now. So they depend on x parameters. So the first operator gets an x parameter. Second one gets an x parameter, and so on. All of the x's are different. And then there is also this q-deformation, which you can think of as a twist, if you like. So there is some operator here, which turns out to be a diagonal operator that introduces the q parameter that was in the previous relations. And so by explicitly constructing all of these operators, we showed that they actually satisfy the relations given on this slide here. And therefore, this provides a valid partition function formula for the polynomials. And it's really an honest formula in the sense that you can take these matrices and put them into a computer and go ahead and compute the polynomial, and you get what you want. All right, so this is a kind of pictorial representation of what's going on. So I certainly wouldn't expect anyone to get the full picture from this depiction here. But effectively, the idea is the following. So this is the original ring that we had for our process. And I have particles that occupy the various sites along the ring. And what's going to happen now is each one of these particles is going to then propagate along a cylinder. So I sort of complete the original ring by attaching to it a vertex model, a cylinder which you can think of as having arbitrary length. And what happens is the colors, they come in and they start to go through this cylinder, and they're allowed to wind around it. But ultimately, they have to leave somewhere, and the position where they leave is basically equal to their color. So for example, if I have this one that has color 2, it comes in and it will ultimately terminate, that is, exit the cylinder via some sort of cut in column 2. Likewise, the color 3 particles will exit in column 3, so on and so forth. So this is an honest partition function in the sense that each one of these squares here is a vertex weight. And it happens that the vertex weights are exactly the ones that were just shown in Ivan's talk. So when he spoke about the colored Q-boson model, that is precisely the model that is being put on this lattice here. Except that in Ivan's case, he was using Q, and here I'm using T. All right. And there is one other important thing to say about this, which is that so these colors, as I mentioned, they come in and they wind around the cylinder. Every single time they wind around this seam here at the top, there is a penalization, and you pick up a Q power, a Q factor. That's exactly the Q that appears here. Okay? All right. Any questions? Yes.
Red color is winding once, right?
The red color is, it can wind in all of the first 3 columns. Yeah.
Yes, but in your particular picture, it's winding wide because it's constrained by the green color. Is it correct?
No, there's just an example. So here there's no constraint. It can go wherever it wants. Yep.
Is there any kind of symmetry between Q and T?
Yeah, that's a very good question. So in this picture, not yet, but we're about to see such a symmetry coming up. Yeah.
Michael, can you prove the stationarity of the matrix product space by using this picture?
Yes, absolutely. I mean, the fact that this thing in the limit gives you the stationary distribution effectively follows from looking at the degenerations of these relations here. So, as I said, Ti you can think of as being an inhomogeneous generalization of the ASEP generator, at least the local generator. Right? So basically, these rules here, you can use them to show that in the limit, this thing is indeed going to be the stationary distribution. Yeah. Actually, all we're really doing, or all we really did, was to rewrite the original formula here, but generalize these things to include the parameters. So in the limit where x and q goes to 1, you recover exactly this formula. So,
this I understood, but the proof of the stationarity may be understood by looking at the figure.
Well, I'm not so sure about that per se.
Oh yes, we did that using Jan Baxter. We can encode, if you forget about the q but keep the parameters x, you can encode the T operators as crosses, and then you can actually attach on the left. You can attach a stochastic six-vertex model, and you can commute it through the cylinder using MX.
Okay.
Sorry, Michael, I have another question. So you said the vertex weight is SL hat M, right? Where I guess M is the ring. So
M is the sort of number of colors, yeah.
Oh, it's the number of colors. Okay, so that's how it's built into the.
Yeah.
Okay, that makes sense. Thanks.
Okay. All right, and actually, yeah, I mean, I should say as well that in the paper of Leo and Matthew and Amal, they also formulated these results, and probably in a much more precise manner than in the original text. So certainly very grateful that they did that. Yeah. All right. So sort of as a trivial consequence of some of the previous facts, you actually can end up getting a partition function formula for the symmetric McDonald polynomials. And really, you should think of this as being like the normalization that you need to correctly normalize these sort of generalized probabilities. Okay, so I'm going to now sum up all of the F mu's, where I sum over all compositions such that the sort of positive reordering of the composition gives you a partition lambda. So really, this steady state distribution splits it very naturally into sectors, where the sector is basically the number of particles you have of each color, because you're on a ring, so particles can never leave or come in, so the types of particles that you start with will persist through time. So by summing over all of the compositions that live in that particular sector, you get this formula for symmetric McDonald polynomials. And that follows from the fact that, as I mentioned here, when mu is equal to a partition, this is actually a non-symmetric McDonald polynomial. And by the general theory, if you symmetrize over such a family of objects, there is basically a unique symmetric polynomial in that sector, if you like, which is the symmetric McDonald polynomial. So there's some uniqueness theorem that allows you to conclude this. And just going back to the picture, not much changes. So I've sort of dropped the paths now. But effectively what you have is, again, you have your particles that live along this ring. And now, instead of having a precise configuration of particles along that ring, you have free boundary conditions. You have to sum over all ways for the particles to distribute themselves along the ring, which is exactly performing this sum here. Okay? So that's why I put this free boundary conditions here. And the type of boundary conditions is, of course, indexed by lambda. That tells you the number of different particles of different colors that you have. Okay. So I'm going to use this kind of schematic on a couple of the slides that follow. And really, the things I want to point out here are the spectral parameters, the x's, which live along the rows of the lattice. There is this q parameter that, as I mentioned, lives along this seam of the cylinder. And there is also the t parameter, which is the quantum group parameter, and that somehow lives in the bulk. Okay. All right, so now let's generalize things a little bit, and this will actually bring me closer to answering Philippe's question from a bit earlier. By the way, how am I going for time? Can someone tell me? 10 more minutes, okay. Yeah. All right, so a lot of this material was generalized in a paper with Sasha from 2018. Effectively, what we did is we took the previous setup and we actually performed what's called fusion of the lattice lines. And at the level of the underlying particle processes, what you get now is a particle process where at every single site you can actually have multiple particles. Instead of just one particle, you have arbitrarily many particles of arbitrarily many different colors. And these have been studied quite a bit. These are the so-called zero-range processes. Okay, and very well studied, and there are also papers that look at the stationary distribution of such processes. But we were sort of interested in the continuation of the earlier work from paper with Luigi and Jan. And what we did is we constructed a family of polynomials, which we call W polynomials. And they have, very naturally, an extra set of spectral parameters that you get here. Now, these are not really spectral parameters. They're actually related to, when you perform fusion, you get some parameter here that is actually the level of the fusion that you perform. So this is somehow related to the level of the fusion. So I'll have now a family of X and a family of Zs that sit along the rows of the lattice. And once again, I have these free boundary conditions here. And I'm not just summing over, single particle at every single site, having a particle or not. I'm actually summing over all ways to distribute the particles such that they can occupy the sites as much as they want. Okay? So there is such a formula. And sort of the reason we got interested in this is these W polynomials, they're actually very nice. So they correspond to, they're effectively what you would call supersymmetric analogs of the Macdonald polynomials. And you can define them very simply. You take a Macdonald polynomial and you perform what's called plathistic substitution. You send the pkth power sum to some other combination of power sums. And this has the property that if you set the secondary alphabet, the zi's, equal to minus t times xi, you actually recover just the usual Macdonald polynomials. So they're going to be Macdonald polynomials, but they have now 2 alphabets. And there is a very important property of these polynomials, which we were certainly struck by at the time, but I don't think we expected it would have such nice consequences, which is this symmetry property that if you take W lambda and replace lambda by the conjugate, by its conjugate, and in the process of doing this, I also switch the X and Z alphabets and the T and the Q. Then those 2 objects are equal. And this is sort of a property that is actually totally outside the realm of vertex models, at least at the moment. So the proof of this property boils down to looking at the Cauchy identity and the dual Cauchy identity for this family of objects. And to date, we do not have a Yang-Baxter proof of the Cauchy identity for Macdonald polynomials. So this is somehow really outside of what we know how to do. And this is a very nice, very deep property of these objects. And we're going to look now at one consequence of this.
Sorry, this is just a Macdonald involution, right? Basically.
Well, it is effectively that, but transcribed to the level of the super objects. So, yeah. Well, so Macdonald involution, when you apply it to ordinary Macdonald polynomials, yeah, it's a map, whereas this is really saying the 2 things are equal. So it's somehow stronger. All right, so if I take that previous equality and degenerate it to Macdonald polynomials. Okay, so on the one hand, I'll set the z's equal to minus tx, and I get this. So this is actually the formula that I showed a couple of slides back. This is the known formula. But if you use the other side and perform the same specialization, you get this formula. Now, they might look totally equivalent, but there are some important differences here. So the first difference is that the way the spectral parameters are implemented is different here. The second difference is that in the bulk, this has a t parameter. Here, this has a q parameter. And third difference is that in the twist, here you have a q and here you have a t. So this is actually a very non-trivial relationship between these 2 partition functions. And to date, there is absolutely no known bijection that will take you from one side to the other. All right, so what we did in the paper with Jimmy was to look at a very, very special case of this correspondence. So we're going to trivialize a lot of stuff. So the first thing we'll do is we'll set the t parameter equal to 0. We're going to choose the partition that appears here to be basically a rectangular partition. And then look at what happens to this correspondence. And just in a nutshell, what happens on this side, the vertex model that you get in the bulk becomes something very, very simple. It's effectively what's called the phase model. I don't know if anyone is familiar with this terminology. It's kind of a physics name. This model has been studied previously. And it's a very, very simple model. Whereas if I set t equal to 0 on this side, that will have no effect on what happens in the bulk, but it will actually kill the twist parameters here. So what you end up getting is a relationship between a sort of cylindrical partition function and a planar or flat partition function. And that's exactly what I showed on the very opening slide of the talk. All right, so in the remaining probably 2 minutes, I'll show in a little more detail what happens. So on the left-hand side, which I'll call Formula 1, basically as I said, you take t to 0, you take your partition to be a rectangular partition, and you get, well, this partition function shown here. So I have basically a family of paths that enter from the left, and then they're going to, at some stage, go through the lattice, and sometimes they will wind. And every single time they wind, you get a power of q. The power of q that you get is indicated at the top of the column here. And eventually they'll go out, and they go out all at the same position. Now the reason they all leave at the same position is I'm choosing this very particular choice for my partition, rectangular partition. So they all have to go out there. And the weights of the model, very simple. Basically, they're all equal to 1 or x. So you couldn't get much simpler than that. All right. On the other side, it's slightly less trivial. So as I mentioned, on the other side, q will survive in the bulk model, but the twist parameters will die. So this is no longer on a cylinder. You have some collection of paths, again, that enter via this left boundary, and then they propagate through the lattice. And because of the particular nature of the model in this case, the sort of appearance of the paths looks quite different when you actually plot them. And I want to say it looks a lot like the line ensembles from Ivan's talk. Maybe there is more to say there. Anyhow, these are the weights. Again, they're relatively simple. You have just a pure power of x that basically keeps track of the number of paths that go through this right edge. And there is also just a q binomial. So in particular, this is a positive formula for q-Whittaker polynomials because you just have pure monomials in x and also positive powers of q. All right. So essentially, with a little bit of work, and this is really the part where I'm sort of sweeping some details under the rug, you can then show that those two partition functions actually equate to what's shown on the right-hand side here. So the first formula, which was with this one, effectively what you need to do is just draw a sort of dividing line somewhere along here. And you're going to think of everything below the dividing line as being one skew Schur polynomial, and everything above the line as being a second skew Schur polynomial. And these sort of q factors that you pick up from going around, they end up being precisely this q factor here. It's not too difficult to prove this statement. And likewise, in the case of 2, this ends up basically just being sort of a straight Cauchy identity for q-Whittaker polynomials, except that it's kind of in a finite situation instead of infinite situation. But the matching of the partition function that you get here, so again, if I draw a line and look at everything below, that will give me one q-Whittaker polynomial, and everything above there will give me the second q-Whittaker polynomial. And these facts were sort of explored in a couple of papers. There was a paper by Christian Koff where he gave a lattice model formulation of q-Whittaker polynomials, and later in a paper with Alexei, we sort of rediscovered some of these facts. So, all right. So effectively, by equating those two sides, which, as I as I've mentioned, these two things are equal, you do therefore get a proof of the IMS correspondence. Okay. All right, so final slide. I don't think I would do full justice to the work with Jimmy without actually mentioning probably the most important part of the work, which is that we actually generalize the correspondence, which is in the following theorem. So effectively what you do is you sort of mix the two notions that we've seen together. So on the one hand, you had a periodic Schur process. On the other hand, you had q-Whittaker processes. So what if you consider periodic q-Whittaker processes? Then you will get this kind of expression. So in this expression, you have a product of two skew q-Whittaker polynomials, and there is also some sort of winding fugacity that now depends on a different parameter, t. And it turns out that that quantity there is actually qt symmetric. And we proved this, not using vertex models, by some independent methods. And effectively taking this, this result and then setting t equal to 0, you recover precisely the IMS correspondence. So I think I will stop there. Thank you.